Hey guys, welcome to my lab report for Physics 2211 Lab 1. Today's lab covers Newton's second law and the momentum principle as I roll a ball at a constant velocity. Newton's second law explains that the force applied to an object is equal to that object's mass times its acceleration. This can also be described in terms of the momentum principle. The momentum principle states that a change in momentum is equal to the mass of the object times its change in velocity. Using these principles, it can be deduced that when an object is traveling at a constant velocity, there is both no net force being applied to that object and no change in that object's momentum throughout. This lab occurs at a constant velocity, so there's not actually a net force being applied to the soccer ball, but that doesn't mean that there's no force at all being acted on it. It's actually the opposite. The forces of gravity, the normal force, the force of friction, and what I like to call the force of push that I apply to the system all work together to keep this ball at a constant velocity. Each force balances the other out so it doesn't have an effect on the rolling ball. I'd also like to bring to your attention the plus and minus signs on the diagram. Those represent which direction in each axis is positive and which is negative. There will be more on that later. I decided to conduct my experiment by rolling a ball down the hallway of my dorm, like you see here. An 8.5 by 11 piece of paper was used as a length reference. I began the video and pushed the ball so that it would travel through the frame at a constant velocity, then I exported that video to Tracker so that I could analyze the data. My location ended up being a great place to film because the trim on the bottom of the floor provided a uniform reference of the height that I could use when analyzing my data. Adding to that my decision to measure the points of the ball from the left side of the ball instead of trying to find the center of the ball, I ended up having a very precise measurement of the data. After collecting the experimental data, I moved on to generating my theoretical model. I just wanted to take a second to explain some of the code that was used to make my model. I began by weighing the soccer ball, which was about 0.43 kilograms, and assigning that to the variable ball.m. I set the initial conditions to the following values, only changing the x component of the vector because that is what we were focused on in the experiment, so the other values of the y and the z-axis should be negligible. I next set the initial time and the time step between each data point. Because the ball should be traveling at a constant velocity, I had to adjust the force vector to be 0 since there should be no net force acting on the system. Lastly, I had to adjust some of the code for the momentum principle section because the original code did not include the change in time, or delta t, and the position equation additionally needed the velocity variable to be included in the code. Once the code was finished, I ran the model and collected the data that I would later use to compare with my experimental data. Looking at both my model and my experimental video, it is clear that both look very similar, which confirmed that I had coded my model correctly. Comparing the dataset from both the model and the experimental data, a similar conclusion can be reached. Firstly, I want to point out some elements of the graph. Notice that there are both positive and negative values exhibited on the y-axis of the position time graph. This occurred because I did not move the axis feature in Tracker to begin at the initial position of the ball. Ordinarily, I would have changed this to make the position-time relationship a little clearer, but since we were ultimately focused on the average velocity, which is the slope of the position-time graph, it didn't seem necessary to change the location of the origin. Because of this decision, some very interesting observations can be made about the axes of my data. For this experiment, I chose the left of the origin to be negative and the right of the origin to be positive. Had I changed the signs, the graph would have looked entirely different. The data would have started negative and proceeded to go positive, and the velocity would instead be positive, like in this graph here. Additionally, I included the equations for the line of best fit for both sets of data. You can see based on the r-squared value that both the experimental and theoretical data support the claim that the ball was moving at a constant velocity. For if the data fit a nonlinear curve better, then the velocity would not have been constant in the experiment. Because the velocity was shown to be constant, this experiment supports Newton's second law and the momentum principle, because the final velocity minus the initial velocity would equal 0, meaning that there was no change in momentum and no acceleration of the object, which also says that there is no net force applied to that object. Looking at both the experimental and theoretical data a little closer, you can see that the slope of the experimental data curve becomes slightly steeper than the theoretical data as time passes. A major reason of why this might have happened stems from the surface the ball was rolled on in my experimental data. Remember earlier when I described the forces that were acting on the ball as it rolled through the frame. It is possible that because the carpet the ball was rolled on had a high coefficient of friction, that as time passed, the force of friction began to overcome the force of the push I gave it, and that caused it to slightly slow down as it got towards the end of the camera view. So that about wraps it up for today's lab. Hope this lab helped you understand the Newton's second law and the momentum principle a little better.